The receiver main subcircuit. This course will be in three parts, as we discussed earlier: the receiver, the transmitter, and the board generator. The receiver data reception occurs in four stages, which is controlled by the receiver finished state machine, also called the RX-FSM signal. At stage 0, this is the idle stage, nothing occurs here. At this stage, if the receiver receives the start bit or a low from the transmitter, it immediately goes to stage 1. The receiver keeps alternating between stage 1 and stage 2 while receiving data until it receives a total of 18 data bits. Then it moves to stage 3. At stage 3, if the stop bit is on, the receiver halts at this stage and nothing happens. Else, if it's off, it goes to stage 0 and continues data reception from the beginning. Now, the Vhdl code. The first part of this Vhdl code is the Vhdl standard libraries. Next is the receiver port, including the stop signal, RSB signal, clear to send signal, board clock, reset, clear clock signal, the data in, and the error signal. Next, the parity generator component, which we will add. This is used for error detection. The parity generator takes our received data bit and generates a parity bit from it. Then it compares this generated parity bit with the parity bit which was received from the transmitter during data reception using a XOR gate. If they are not the same, then an error signal comes on. I'll show you the main circuit of the parity generator. It's simply a 16-input XOR gate that takes a 16-bit data and generates a XOR gate signal from it. Next is the signal. We'll discuss them later. Again, the DIN, no bits or number of bits, the clear clock signal, and the error signal. The DIN is the final received data which comes from the data register. The no bit signal triggers the RX-FSM or the receiver finished state machine to move to the last stage. That is when it's still fluctuating, when it's in stage 2 or stage 3. Whenever this no bit signal comes on, it moves to the last stage. This bit comes on whenever the number of received bits, also called the RS bit count signal, is equal to 18 in decimal or 11 in hexadecimal. The clear clock signal. This signal is used for oversampling, which we discuss when we are talking about the board generator. It signals the start of data reception, which is when the RX-FSM is in stage 0 and the RS bit line receives a low bit or a 0. Then, the error signal. This compares the parity bit generated at the receiver and the bit 1 of the received data, which is the parity bit that was received from the transmitter. Next, we have the registers, including RX-FSM register, RS bit count register, error register, and the data register. RX-FSM, this register stores the receiver state. The RS bit count register, this register stores the number of received bits, which is used to generate the no bit signal. Error register, this register stores the error bit. Finally, the data register, this register stores the received bit. Then next, the state machine. We have stage 0, stage 1, stage 2, and stage 3. This is the case statement which can be represented with a multiplexer. At stage 0 or idle stage, if the RS bit, which is usually high, receives a start bit or 0, and the CTS or clear to send signal is on, then the RS bit count register is reset so that it can start counting from 0, and then the state moves to stage 1. At stage 1 and stage 2, stage 1 and stage 2 do exactly the same thing. They just alternate between each other while the RS bit count keeps incrementing and the receiver is receiving the data bits. And then the data register, which is a shift register, keeps receiving the received bits and shifting it to the data register called DIN. And whenever the RS bit count register equals number 11 in hexadecimal or 18 in decimal, then it moves to stage 3. If the stop bit is on at stage 3, everything halts here, else the RX FSM moves to stage 0 and data reception starts afresh. Also, at this stage is when the error bit is calculated. This AND gate enables the generated error to trigger at this stage. So this is the logic behind the receiver subcircuit. The full code will be attached to this lecture. In the next tutorial, we'll discuss about the board generator.